This is question 17 from the 2012 PAT, and in this question we have a slider moving along a track. We're told the slider has mass, there's no friction with the track, the starting point S and the point T at the top of the curve are at the same height as shown by this line, and also this part of the track is circular. So some of these facts might be more relevant than others, but we'll have to see which are which as we go through. And what are we actually asked? Well, we're given 4 options for what happens to the slider. So A is that it never gets to T, B is that it goes around, gets to T and then falls straight down, C is that it goes around, gets to T and then follows a parabola to the left, and D is that it does the same thing but it stays on the track, the circular track past T. So if you want to have a go at figuring out which of these is correct yourself, pause the video now. Okay, so there are a couple of ways to think about this, but I think a natural one is if we have a massive object moving, we're either dealing with forces or energy. And in this case, we're given a piece of information that these 2 points are at the same height. It isn't really relevant to the forces on the object, but is directly relevant to the energy because that says the GPE at these 2 points is the same. So let's see if we can use that to help answer the question. Okay, so which option should we look at first? I think it's easiest to look at C or D, so let's start with C. And what does that look like? Well, it's something like this, it goes around the track, gets to T, follows a parabola to the left. And if we're thinking in terms of energy, there's no friction, so there's no energy lost to friction. So if we think about the initial gravitational potential energy and initial kinetic energy, the sum of those is conserved. So at the start, we could measure the GPE from anywhere, but let's just measure from the bottom of the picture. So if we call this height h, it starts off at mgh, and the initial kinetic energy, why is that 0? Well, because this is the start, so it's not moving yet. So it's got speed 0 and therefore 0 kinetic energy. And t is at the same height. What does that mean? Well, it means the GPE is the same. And because energy is conserved, what does that mean? That means the kinetic energy has to be the same as well. But that would mean it would have 0 speed at this point. But if it follows this trajectory, it's moving through the point T and to the left, and therefore it doesn't have 0 speed. And that means we can actually rule out this case. And D is very similar. D looks like this, so it's exactly the same except it stays on the track instead. But that still means it's moving through the point T with some positive speed, and therefore we can rule that out as well. Okay, so now let's look at B, which is that it gets to T and then falls straight down. Okay, so that looks something like this, and this initially seems similar, but actually in terms of energy it's okay, because at this point we can say it has 0 speed before it starts falling, and therefore the energy works out. But this should look suspicious because we don't normally get these sharp corners in trajectories in nature, unless it's a collision. But how could we show this can't actually work? Well, if thinking about energy doesn't work, we could think about forces instead. And in particular, I'm interested in, let's think about the velocity of something following this trajectory as it goes around this part of the curve. Here its velocity is going to be, it's going to be tangent to this curve, so it's going to be up and to the left, and it's going to have positive speed, and here it's going to have 0 speed. And its velocity is changing, so that means it must be being accelerated, and therefore there's a force. But what direction should the force be acting in? Well, in particular, if we think about the horizontal component, here the horizontal component of the velocity is to the left, and here it's got 0 velocity, so in particular it's got 0 velocity to the left. And that means that there must have been some force acting to the right to slow it down in that direction. But what forces are acting on the slider, on this part of the track? We've got the weight acting down, we've got the reaction from the track which acts down and to the left towards the centre, so neither of those is acting to the right, and therefore this is actually impossible. It can't slow down. Okay, so we better hope that A is the answer, but let's just have a look at that option too. Let's just remind ourselves that A says it never gets to T at all. So what does that look like? Well, I think one thing that's tempting to draw is this. So suppose it goes around here and then it gets to here and it's not going fast enough to keep going up, so it stops and then falls back down. So could that happen? Well, actually, if we think in terms of energy again, this isn't possible. So if we think about its initial energy, this point here is below this point, and therefore the GPE will be lower. So by conservation of energy, the KE should be higher, so there should be positive kinetic energy. But that means it can't stop, because then its kinetic energy would be 0, so it can't stop and fall back down. And that means we can rule out this case. But is there another way that the slider could fail to get to T? Yes, it could look something like this. So it gets to the upper part of the curve and then falls off and follows a parabola to the left because it's in freefall. And this doesn't have the same problem with energy because it's always below this point S, but it's always moving, and that's consistent because we know it ought to have positive kinetic energy. And also it doesn't have the same problem with forces that B had. And therefore this is possible, and so A is the correct answer.